Just for a discussion on inertia, let's say uh, this ring that you are seeing here is a planar version of our spherical universe. I really don't know if our universe is spherical, but that is the assumption which works good. So now let's say we have a ball, and then this ball, if you put it on a weighing scale, it will have a mass, and then you can see that whenever the ball is hit, it tries to follow a straight line motion. The seam is distorting it. Anyway, let's try this ball and then see if you are able to get a straight line motion. Yeah, so more or less straight line. So inertia as a concept is a combination of mass which resists motion, and also very importantly trying to keep the motion in a real straight line. Another important observation is I will not hit this through the CG, but a bit away from it, and still you can see the path of CG here. So though the object is spinning, the CG keeps a straight line. So the resistance to motion due to the mass and also the property to keep it in a straight line motion, the combination is called as inertia. So we'll take one more example. Let's say I try to hit this ball, and because there is a physical boundary, it tends to go around. But alternatively, look at this example, so which is hanging here. So the mass is distributed around, and when I try to move this part of the mass, this mass too wants to keep a straight line. But because the spokes retain it to the center, it doesn't have any other choice than spinning around the overall CG. So you can see this effect of inertia in action, of the property of mass and trying to keep it in a straight line, that when this fellow is tilted and just without spinning, if I leave it, it comes to this equilibrium. But at the same time, if I keep it here and tries to give it a spin, you can see that the inertial property tries to keep an invisible hand like this. Okay, and that's why your cycles and bikes work. Hope this clarifies. So inertia is a combination of the mass which resists motion and also the property to keep the object in a straight line. In days when there were no air glides, or people have not yet reached space, there is no friction. So this is a simple experiment conducted by Galileo, and of course it ends with a thought experiment. Okay, let's start with and see what does the experience do. This one is for measuring the level at this point and this point. So we'll be rolling a ball in this track to observe the behavior. So right now the ball is at this level and is at rest. Let's allow it to roll. On the other side, the ball almost reached this level. Still it doesn't reach the same height because of friction in the surface. Now let's move this a little lower. Okay, and then that gives a rough referral height. That indicates a rough referral height, and we'll release it from the same point and then see what happens. We have not moved this reference line. We'll just see what happens. So we release the ball and it still tries to reach the same level. So let's leave the ball from a little higher above and then see what happens. And the ball almost reaches.
Let's push this to a level which is straight enough and then see what happens. So we have kept this bar almost at the horizontal level, and then allow the ball to roll from the same point, and the ball keeps going and goes over. So Galileo's thought experiment is, if this ball is traveling in this line, it will keep on going, trying to reach the same height from which we release the ball. So this is just a innovative thought experiment on days when there were no air glides, or people have not reached the space travel where there was literally no friction.